As you're watching this, you're literally surrounded by waves. The light hitting your eyes from the screen, that's a wave. The sound coming out of your speakers, also a wave. They are pretty much the invisible architects of our entire reality. So today, we're going to pull back the curtain on the physics of waves.
So think about it for a second. An ocean swell, your Wi-Fi signal, the sound of your own voice. What could they possibly have in common? They seem like totally different things, right? But deep down, they all share the exact same fundamental identity. Yep, they are all waves. But what does that really mean? Okay, so to really get what connects a giant wave in the ocean with the Wi-Fi signal you're using right now, we've got to start at square one. Let's build our foundation and answer the biggest question of all. What, fundamentally, is a wave? Now, that last part is the absolute key. Without permanent displacement of the medium. I want you to picture a crowd doing the wave at a football game. You see this ripple of energy move all the way around the stadium, but each person just stands up and sits right back down. Nobody's running around the arena, right? The people don't travel, only the energy does. And that right there is the very essence of a wave. So if we really want to understand waves, we kind of have to learn how to speak their language. And it turns out every single wave, no matter what kind it is, can be described using just a few key measurements. So let's break them down. This diagram here is like our basic roadmap. You can see the high points, which we call crests, and the low points, or troughs. But to really get a feel for a wave's personality, we need to zoom in on two absolutely crucial properties: its amplitude and its wavelength. Amplitude is pretty much the wave's height or size. For a water wave, a higher amplitude means a bigger, way more powerful wave. For a sound wave, a higher amplitude means a louder sound. So the main takeaway is this: more amplitude equals more energy. It's that simple. Next up, we've got wavelength, which you'll often see represented by that Greek letter lambda. It's really just the physical distance from one point on a wave to the exact same point on the next wave. So for instance, from the very top of one crest to the very top of the next one. And last but not least, we have frequency. Okay, imagine you're standing still in the water and you count how many wave crests wash past you every single second. Well, that's the frequency. And it's super important. For sound, a higher frequency gives you a higher pitch. For light, a higher frequency actually determines its color. All right, now that we've got the basic vocabulary down, let's take a look at the different families of waves. Because it turns out they're not all created equal. We can actually sort them into different groups based on a few key differences. This chart gives us a fantastic family tree, and you can see the very first big split right at the top is based on a simple question. Does a wave need a medium, a substance to travel through, or not? And this is a really fundamental difference. Mechanical waves, like sound or ocean waves, have to have something to travel through. Air, water, a solid wall. If you're in a vacuum, there's no air, so there's no sound. But electromagnetic waves, like light or your Wi-Fi signal, they're totally different. They can travel right through the empty vacuum of space. It's the whole reason we can see the light from the sun. The other big difference is how the particles move. So in a transverse wave, the vibration is up and down, while the energy moves forward, kind of like when you shake a rope. But in a longitudinal wave, the particles actually push and pull back and forth in the same direction the energy is moving, like a slinky being compressed and stretched. Sound is a perfect example of a longitudinal wave. All right, this is where things get really, really interesting. We know what waves are, and we know their different types, but now let's look at how they act, how they interact with the world around them, and with each other. This is the cool part. These 5 properties basically describe the personality of a wave. We're going to see how they bounce, how they bend, and even how they can combine with each other. This is how waves actually shape our world. So let's break down reflection, refraction, interference, diffraction, and polarization one by one. Reflection is probably the one you're most familiar with. It's simple. When a wave hits a barrier it can't pass through, it just bounces off. The reflection you see in a mirror, that's just light waves bouncing back at you. An echo, that's sound waves bouncing off a distant wall and coming back to your ear. Easy enough, right? Now, refraction is what happens when a wave changes speed because it's entering a new substance, and that change in speed actually causes it to bend. This is exactly why a straw in a glass of water looks like it's bent right at the surface. The light waves coming from the straw travel faster through the air than they do through the water, and that little speed change makes them change direction. So cool.
So what happens when two waves run into each other in the same place? Well, they interfere. If their peaks and valleys line up perfectly, they add together and create a bigger, more powerful wave. We call that constructive interference. But, and this is amazing, if the peak of one wave meets the valley of another, they can completely cancel each other out, creating, well, nothing. That's destructive interference, and it's the brilliant physics behind how noise-canceling headphones work.
Have you ever wondered how you can hear someone talking in another room even when you can't see them at all? Well, that's diffraction in action. Sound waves are long enough that they can actually bend around an obstacle, like a doorway, and then spread out, allowing them to reach your ears even when you're around a corner.
Okay, our last property is a little bit special. Imagine light waves vibrating in every direction at once, up and down, left and right, diagonally, you name it. Polarization is like sending that messy light through a filter that has a tiny vertical slit in it. What happens? Only the up and down vibrations can make it through. So here is the absolute most important thing to remember about this. Polarization only applies to transverse waves. That's it. Why? Because longitudinal waves, like sound, are already vibrating in the same direction they travel. There's no other plane of vibration to filter out. This is a huge clue that helps us identify transverse waves.
Okay, so we've gone through all this physics, but you might be asking, why does any of this matter? Well, let's bring it all back home and see how these principles, especially that kind of tricky one, polarization, show up in tech you probably use all the time.
Just look at these examples. Those polarized sunglasses you wear, they have vertical filters that block the horizontal light waves that reflect off surfaces like roads or water, which is what our eyes see as glare. And at the movies, 3D glasses use polarization to send a slightly different image to each of your eyes, which tricks your brain into seeing depth on a flat screen. It's pure physics at work in our everyday lives.
You know, when you think about it, from a simple ripple in a pond to the complex radio waves that connect our entire world, waves are the invisible force shaping our reality. Understanding them isn't just about physics class. It's about understanding how the universe itself communicates. Which leaves us with just one question. What will the next wave of discovery reveal?